deeper into increasingly dense, increasingly hot gas. The atmosphere would gradually thicken around you from a thin haze at the cloud tops to a dense fog deeper down. Then to a crushing pressure that would destroy any spacecraft long before you reached anything resembling a surface. Eventually, at depths of tens of thousands of miles, the pressure and temperature become so extreme that hydrogen, which is a gas at low pressure and a solid at extremely high pressure, transitions to a liquid state. Deeper still, perhaps 15,000 to 20,000 miles down, the pressure reaches millions of times Earth's atmospheric pressure. At these conditions, hydrogen transitions to a strange state called metallic hydrogen. In this state, the pressure is so high that hydrogen's electrons are stripped away from their atoms and flow freely, making the hydrogen electrically conductive like a metal. This metallic hydrogen layer is thought to be responsible for Saturn's powerful magnetic field. Electric currents flowing in this conducting fluid generate magnetic fields through the same dynamo process that generates Earth's magnetic field, just on a vastly larger scale. No spacecraft humanity has ever built could reach Saturn's metallic hydrogen layer. You'd be crushed and incinerated long before getting there. At the core, below all these layers of atmosphere and liquid and metallic hydrogen, there's probably a dense central region. This core is thought to be composed of rock, metal, and exotic high-pressure forms of ice, water ice, ammonia ice, methane ice, all compressed to densities far higher than anything found on Earth's surface. The core might be 10 to 20 times Earth's mass, though it's difficult to determine precisely because we can't see it or directly measure it. Our understanding comes from modeling Saturn's gravity field and how the planet responds to gravitational perturbations. Temperatures at Saturn's core are estimated at somewhere between 20,000 and 25,000 degrees Fahrenheit, or 11,000 to 14,000 degrees Celsius. For comparison, the Sun's visible surface is about 10,000 degrees Fahrenheit. Saturn's core is hotter than that. The pressure at the core is estimated at tens of millions of times of the Earth's sea level atmospheric pressure. At these extreme conditions, matter behaves in ways that are difficult to study because we can't replicate these conditions in laboratories. Materials that are soft and weak at normal pressures become incredibly hard. Chemical reactions that don't occur at normal conditions become favorable. The physics is fascinating, but also means that nothing we've ever built could survive those conditions. No material, no design, no clever engineering solution can withstand tens of millions of atmospheres of pressure and tens of thousands of degrees of temperature. The forces involved are simply too immense. So you can't land on Saturn because there's nothing to land on. You could descend into the atmosphere, but you'd be destroyed by heat and pressure within hours at most, probably much sooner. The Galileo probe, which descended into Jupiter's atmosphere in December 1995, survived for about 58 minutes and transmitted data from a depth where the pressure was about 24 times Earth's atmospheric pressure and the temperature was about 330 degrees Fahrenheit, or 166 degrees Celsius. Then it was crushed and vaporized. Saturn's atmosphere is somewhat less extreme than Jupiter's at comparable depths, but the principle is the same. Any descent is one way. You can send a probe to gather data for an hour or two before it's destroyed, but you can't send humans and expect them to return. And there's another danger we haven't fully addressed yet: the rings themselves. Saturn's rings are one of the most beautiful features in the solar system. They're also a navigation hazard and a source of potential danger that people often don't fully appreciate. The rings aren't solid structures. They're made up of billions of individual particles ranging from dust grain size to chunks as large as houses or small mountains. Most of the ring material is water ice, very pure ice, which is why the rings are so bright and reflective. But there are also rocky particles mixed in, silicates and other materials. All of these particles orbit Saturn in a disk only about 30 feet thick. In most places, despite extending more than 175,000 miles from the planet's cloud tops. That's an incredibly flat structure. If you scaled the rings down so they were as wide as a football field, they'd be thinner than a sheet of paper in most places. The thinness is maintained by gravitational interactions between the particles and by the gravitational influence of Saturn's moons. The particles collide gently, settling into the thinnest possible configuration, like sediment settling in water. But this means the rings are a very dense environment if you're trying to fly through them. The particles are orbiting Saturn at different speeds, depending on their distance from the planet. Inner ring particles orbit faster. Outer ring particles orbit slower. The relative velocities between particles at different distances can be substantial, thousands of miles per hour. If your spacecraft passes through the ring plane, you're potentially encountering particles traveling at high velocities relative to you. A collision with even a small particle at orbital velocities can be catastrophic. A pebble-sized chunk of ice hitting your spacecraft at 10,000 miles per hour carries enormous kinetic energy. It would punch through thin metal like a bullet through paper. It could shatter windows, breach pressure vessels, damage critical systems. Cassini carefully avoided flying through the densest parts of the rings for most of its mission. It orbited at angles that minimized ring plane crossings. Only at the very end of the mission, in its final orbits, did Cassini deliberately fly through the gap between Saturn's atmosphere and the innermost edge of the rings. This was the grand finale, a series of 22 orbits that took Cassini places no spacecraft had been before. The gap between Saturn and the rings is only about 1,500 miles wide. For context, Saturn's diameter is about 75,000 miles. So this gap is only about 2% of Saturn's diameter. Flying through it required extraordinary precision. Cassini had to hit a very narrow corridor, threading between the planet's upper atmosphere below and the ring particles above. The spacecraft encountered more dust particles in this region than expected. Tiny ring particles that had drifted inward, creating a faint, dusty environment even in the gap. These dust impacts were detected by instruments and caused slight changes in the spacecraft's attitude as the particles hit. For a crewed mission, the rings present a serious navigational challenge. You can't just approach Saturn from any direction. You have to plan your trajectory to minimize time spent in the ring plane and to avoid the densest regions. This constrains your mission design. It limits when you can launch, based on where Saturn is in its orbit and what approach angles are available. It affects which moons you can easily reach, because some require crossing the ring plane multiple times. And if something goes wrong, if you have a propulsion failure or navigation error that sends you through the rings instead of avoiding them, you could be destroyed. The rings are also electrically charged. The charged particles from Saturn's magnetosphere interact with the ring particles, creating complex electromagnetic environments. There are spoke-like features in the B-ring, mysterious radial structures that appear and disappear, possibly caused by electromagnetic forces levitating tiny dust particles above the main ring plane. These spokes were first observed by Voyager and later by Cassini. We still don't fully understand what causes them or exactly how they form. If your spacecraft passes through these regions, you might experience electromagnetic interference. Your communications could be disrupted. Your instruments might give false readings. In extreme cases, electrical discharges might damage sensitive electronics. These are risks that can be managed with careful planning, but they add complexity to an already complex mission. The rings also create navigation uncertainty. The gravitational field near Saturn is influenced not just by the planet itself, but by the distribution of mass in the rings. The rings contain a lot of mass, roughly equivalent to one of Saturn's medium-sized moons distributed across that huge disk. This mass creates gravitational perturbations that affect spacecraft trajectories. When you're navigating close to Saturn, you have to account for these perturbations. Your trajectory calculations become more complex. The uncertainties in your position and velocity grow slightly because you're dealing with a more complicated gravitational field. For most purposes, this is manageable. Cassini navigated successfully for 13 years. But for a crewed mission, where precision matters even more because humans are aboard, every additional source of uncertainty is concerning. And then there's the sheer scale of the ring system to consider. The main rings extend from about 4,300 miles above Saturn's cloud tops out to about 85,000 miles. Beyond that are the fainter outer rings, gossamer structures that extend much farther. The E-ring, created by material from Enceladus's geysers, extends from about 112,000 miles out to 360,000 miles from Saturn. This is a huge volume of space filled with particles. Any mission operating in the Saturn system will spend time in or near this environment. You can't avoid it entirely. And every time you pass through the ring plane, even in the thinner regions, you're taking a calculated risk. The radiation environment near the rings is also more complex than in empty space. The ring particles interact with charged particles from Saturn's magnetosphere. Some radiation gets absorbed by the rings, creating a partial radiation shadow. But other radiation processes create new charged particles. Cosmic rays hit ring particles, creating showers of secondary particles. The electromagnetic interactions create plasma and accelerate particles to high energies. The net effect is that the radiation environment near the rings is different from the environment farther away. It's not necessarily worse, but it's more variable and less predictable. For mission planning, this means you can't just use simple models of Saturn's radiation environment. You have to account for the rings and how they modify the particle populations. This requires more sophisticated modeling and more uncertainty in your predictions. What about Saturn's moons? Saturn has 83 known moons, and probably more small ones that haven't been detected yet. These moons range from tiny, irregular chunks of rock and ice, mere miles across, barely more than captured asteroids, to Titan, which is larger than the planet Mercury and is one of the most Earth-like bodies in the solar system, despite being nearly 1 billion miles from the Sun. Surely you could land on one of the moons, explore, gather data, conduct science missions, and then use the moon as a base for your return journey to Earth. This is more plausible than trying to interact directly with Saturn. The moons have solid surfaces where you could actually land. They have gravity, weak compared to Earth, but enough to keep you from drifting away. They provide potential resources, water ice that could be melted for drinking water or split into hydrogen and oxygen for propellant. Some of them are scientifically fascinating. Titan, the largest moon, has a thick nitrogen atmosphere, thicker than Earth's, with surface pressure about 1.5 times Earth's sea level pressure. It has lakes and rivers of liquid methane and ethane. It has weather, clouds, rain, seasonal changes. It has complex organic chemistry happening in its atmosphere and on its surface that might give us clues about the chemistry that led to the origin of life on Earth. Enceladus, one of the smaller major moons, has geysers erupting from cracks near its south pole. These geysers shoot water ice and organic molecules into space at high velocity. Cassini flew through these plumes and analyzed their composition, finding evidence of a subsurface ocean beneath Enceladus's icy crust. This ocean is in contact with the moon's rocky core, meaning there could be hydrothermal activity, chemical energy sources, and all the ingredients necessary for life as we know it. If there's life anywhere in the solar system beyond Earth, Enceladus is one of the top candidates. Other moons like Dione, Rhea, and Iapetus have their own interesting features. Strange surface markings, ancient impact craters, mysterious brightness variations. But landing on Saturn's moons doesn't solve the fundamental problem of getting back to Earth. In fact, in some ways, it makes the problem worse. Here's why. Getting to Saturn requires enormous amounts of energy. You have to accelerate your spacecraft to high velocity, tens of thousands of miles per hour, to make the journey in a reasonable time frame. 7 years is already a long time. If you used less propellant and a slower trajectory, the journey could take 10 or 15 years, or even longer. Nobody wants a 15-year journey each way, so you need to go fast. Going fast requires energy, which in rocket terms means propellant. When you arrive at Saturn, you're moving very fast relative to the planet. If you do nothing, you'll just fly past and continue into the outer solar system, which doesn't help. To go into orbit around Saturn or land on one of its moons, you need to slow down. This requires firing your engines in the direction you're traveling, using your propellant to reduce your velocity. This is called a capture burn, or orbital insertion burn, and it requires a lot of propellant. If you're planning to land on a moon, you need even more. You slow down to enter Saturn orbit, then slow down more to match the moon's orbit, then slow down more to descend to the surface. Every bit of this requires propellant. And here's where the physics becomes cruel. That propellant has mass. And that mass has to be carried all the way from Earth. To carry more propellant, you need a bigger rocket. But a bigger rocket with more propellant has more mass. More mass requires more propellant to accelerate, which increases mass further, which requires even more propellant. The rocket equation, as we discussed earlier, compounds exponentially. For a one-way mission like Cassini, this is manageable. You use all your propellant budget for the journey out and for operations at Saturn. You don't need to save anything for a return trip because you're not coming back. For a crewed mission that needs to return, you face a much more difficult problem. You need propellant for the journey to Saturn. You need propellant for capture into Saturn orbit. You need propellant for operations around Saturn, moving between moons, adjusting orbits. You need propellant to lift off from a moon's surface if you land. You need propellant to escape from Saturn's gravity well. And you need propellant for the journey back to Earth. All of this propellant has to be carried from Earth, or you need to manufacture it at Saturn using local resources, which we'll discuss shortly. If you're carrying all the return propellant from Earth, the mass of your spacecraft at launch becomes astronomical. Let's run rough numbers to see how this works. Suppose your spacecraft has a dry mass, the mass of the structure and equipment without propellant, of 100 tons. That's probably optimistic for a crewed interplanetary spacecraft with all necessary systems, but let's use it. Chemical rockets, the type we currently use, have specific impulses around 300 to 450 seconds, depending on the propellant combination. Specific impulse is a measure of rocket efficiency, how much thrust you get per unit of propellant. Using the rocket equation, if you want to achieve a velocity change of, say, 10 kilometers per second, which is roughly what you'd need for various phases of a Saturn mission, you'd need about 4.6 times the dry mass in propellant. So, 100 tons of spacecraft needs 460 tons of propellant. That's your spacecraft mass before the first burn, 560 tons. But you need multiple burns. One to leave Earth orbit, one to adjust your trajectory mid-course, one to capture at Saturn, multiple smaller burns for operations, one to leave Saturn, one to capture at Earth on return. Each burn requires propellant, and the propellant for later burns has to be carried during earlier burns, adding to the mass that must be accelerated. When you work through the math carefully, the numbers explode. A crewed Saturn mission, using chemical propulsion and carrying all propellant from Earth, would require launching thousands of tons into orbit. The launch costs alone, at current prices of roughly $10,000 per kilogram to orbit, would run into tens of billions of dollars just for the propellant. That's before you count the cost of the spacecraft itself, the development costs, the operations costs, the ground support infrastructure. You're looking at a mission that would cost several $trillion. For comparison, the International Space Station, the most expensive single object ever built, cost roughly $150 billion over its development and construction phase. A crewed Saturn mission might cost 10 to 20 times that. The economic case is difficult to make. One way to reduce the propellant requirement is to use more efficient propulsion systems. Nuclear electric propulsion, or ion drives, can achieve much higher specific impulses than chemical rockets, sometimes 10 times higher or more. This reduces the propellant mass significantly. But these systems have their own problems. They produce very low thrust, so acceleration is gradual. A journey that takes 7 years with chemical rockets might take similar or even longer with ion drives, though the propellant savings would be substantial. The technology is also less mature. We've flown ion drives on robotic missions, but never at the scale needed for a crewed interplanetary spacecraft. Another approach is in situ resource utilization, the idea of manufacturing propellant at your destination using local materials rather than carrying all propellant from Earth. This is theoretically possible and is a key part of many Mars mission concepts. For Saturn, the idea would be to land on a moon like Enceladus or Titan, extract water or hydrocarbons, and manufacture fuel from these local materials. Water can be electrolyzed, split using electricity into hydrogen and oxygen. Both are excellent rocket propellants. Liquid hydrogen and liquid oxygen are what the Space Shuttle main engines used. Methane and oxygen also make a good propellant combination, and Titan has abundant methane. But the equipment needed to extract, process, and store these materials is massive, complex, and has never been demonstrated at the scale required for a crewed interplanetary mission. You'd need power sources, probably multiple nuclear reactors, generating hundreds of kilowatts or even megawatts of electricity. Solar panels won't work well at Saturn's distance from the Sun. The sunlight there is only about 1% as intense as it is at Earth, so you'd need massive solar arrays to generate meaningful power. And they'd be vulnerable to damage from micrometeoroids and radiation. Nuclear is the only practical option. You'd need chemical processing plants, equipment to drill or mine ice, pumps to move liquids, electrolyzers to split water, compressors to pressurize gases, cryogenic storage tanks to keep hydrogen and oxygen, or methane and oxygen, at the extremely cold temperatures required to keep them liquid. You'd need all of this equipment to operate reliably in Saturn's harsh radiation environment at temperatures that can drop to -300 degrees Fahrenheit or colder. And you'd need redundancy because a single critical failure could strand you.
Good night, good night, good night, good night. I'm feeling tired today, but I'm fine. I wanna be good. Voy a dormir como un baby. Good night, everyone.